Okay, so number 21. The graph shows a cooling curve for a substance which starts in the gaseous state. During the 8 minutes shown, the substance first condenses and then solidifies. At what time had all the gas condensed into a liquid? All right, so remember that the flat portions of the graph represent when it is going through a change of state, okay? And the first change of state that we're told is happening here is condensation. It is changing from a gas to a liquid. So in this section here, we have condensation going on. So that means that we have two states of matter present at the same time in this section. We have gas plus liquid, okay? Gas is turning into a liquid, but not all of them have completed the change of state yet, okay? All right, the sloped portions of the graph are where we have only one state of matter present, okay? That means that they are all, none of the particles have reached the next stage yet. They haven't got enough kinetic energy, they haven't reached a high enough temperature, or in this case, a low enough temperature to undergo that change of state. So we have it cooling until it's cooled and lost enough heat to become a liquid. So we have liquid only in this section. Okay, and then at this point, this is our freezing point. This is where the first liquid molecule turns into a solid. So again, we have a mixture of states here. We have solid and liquid. And then in this last section, everything has completely solidified and we have solid only. All right, so we're being asked, what time had all the gas condensed into a liquid? Okay, well, that would be at the end of this process right here. Remember, the beginning of the flat portion is when the first molecule has changed over into that next state of matter. Okay, so if this graph, if we were to continue it, here we would have gas only. And at that point would be where the first gas molecule turned into a liquid. And it continued on until this point when all of the gas molecules are now liquid, and they stay that way until they cool down enough to get to the next change of state. Okay, so that happens at 2 minutes. So our answer is A. Number 22. A man blows over the top of a hot cup of tea to cool it. What is the most likely cause for this cooling effect? A, increased rate of conduction, B, increased rate of convection, C, increased rate of evaporation, or D, increased rate of radiation. Okay, so conduction, convection, and radiation are all ways to transfer heat. So that's going to add heat. But our question told us that this cup is cooling, okay? The only one of these that has a cooling effect is evaporation, okay? Changing from liquid to gas. The only one of these that has a cooling effect is evaporation, okay? Now, this is not to be confused with boiling. Boiling is the change of state that happens only at a specific temperature, at 100 degrees Celsius. But evaporation can happen whenever you have, for example, wind blowing over the surface of a liquid. It gives the liquid molecules enough energy to break away from the surface, and that has a cooling effect. All right, number 23. A 60-watt light bulb is 5% efficient. How many joules of light energy will be released by the light bulb in 1 second? What does this mean? 5% efficient. This means that this is the percentage of useful work that this device will do. Percentage of useful work, okay? So of the total energy, we're going to have 5% of useful work. What's the total energy? Well, it has a power rating of 60 watts for every 1 second that it's on. Energy is equal to power multiplied by time. So the power is 60 watts by 1 second, 60 joules of energy total. Okay, and of that 60 joules, 5% is useful work. So 5% of 60, okay, to do that, you plug in 0.05 on your calculator, multiply that by 60, and you'll get 3 joules. Okay. Number 24, which of the following examples is considered to be an example of potential energy? Okay, remember there are two types of energy, potential, and the other one is kinetic. Potential energy is when objects have stored energy by virtue of their shape or position. So if something is high off the ground, it has potential energy. For example, an apple in a tree, that's gravitational potential energy. If something is pressed, like squeezed or stretched, when you let it go, then it will use energy and it can release that energy. So that is an example of potential energy. Let's look at these options. Okay, we have A, elastic energy. Well, that's the type of energy possessed by rubber bands and springs. They're stretched, they're compressed. So, like I said, that would be an example of potential energy. But let's not stop there. Let's rule out the others, okay? What is light energy? Well, that's the movement of electromagnetic radiation in the form of waves, okay? So that is a form of kinetic energy, movement. Kinetic energy, that's the big category right there. Anything that has energy by virtue of being in motion, okay, that falls under kinetic energy. Sound energy, that one might be a little tricky for you to remember. But remember, sound is produced by vibrations of molecules, air molecules, solid molecules, and anything that vibrates produces a sound. So that is also a form of kinetic energy. So our answer is A, elastic energy. Okay, so this question requires a little bit more thinking, but if you understand refraction, then it's not that hard. So there are two ways that you can approach this. If you've done this experiment, then you might recognize the diagram easily, the same way you might remember what the magnetic field of a bar magnet looks like, because you've seen that before. This one, if you haven't done this experiment, you can still use your knowledge of refraction and just some logical reasoning. So let's take that approach, because most likely a lot of you may not have had the opportunity to do this experiment, but we've all learned about refraction. Remember, refraction is the bending of a light ray when it moves from one medium to the next. Now, there are some rules that we can remember. We're familiar with terms like angle of incidence, angle of refraction. The angle of incidence is the angle between the normal, those are the lines in red and blue that I've drawn. The normal is an imaginary line that is drawn 90 degrees to the surface, and we measure the angle of incidence. So the angle between the incident ray, the one that goes in to the new medium, and the normal, that's called the angle of incidence. And the angle that emerges, the angle between the ray that emerges, so that's our reflected ray, and the normal is what we call our angle of reflection. And that's going to be the key here for us to remember what's supposed to be happening when we have this sort of double refraction going on. Because we got one refraction when the light ray goes into the prism, and then we have another one when it comes out. So it can be kind of tricky, but what you want to start off with in a question like this, you want to draw in the normals, okay? If you aren't sure, how am I going to measure 90 degrees, right now, what if I don't have a protractor? Well, just take your ruler and you just line it up along the edge. So if this is, I'm going to draw one of the triangles over here. Okay. 1 second. Okay, so you're in the exam, you got your ruler, take your ruler, line it up on the edge there. And that line, it's a lot straighter, but that line is your normal, right there. Okay, you just line it up along the edge of that line. Okay, so I've drawn in the normals for all of these prisms. And what we want to look for is, we're going to remember that when a light ray is going from a medium where it's going to travel slow So that will be the one that's more optically dense. So if you go into a more dense medium, then the light ray travels slower. If you go into a less dense medium, the light ray will travel faster. In this case, the more dense medium is the glass prism. So when it's going into the glass prism, it travels slower. And when it's coming out, it's going to speed up again when it's traveling in the air. So slow to fast, we're looking for a bigger angle of refraction, okay? It bends away from the normal when it is going to a faster medium, going into a faster medium. Faster to slower, so let's say from air to glass, the angle of refraction gets smaller, okay? So I've drawn in the normals. The normals for the incoming rays, so for the first one are in red and for the second one are in blue. So let's look at what's happening in each case. So in A, we see that the angle of refraction, the angle of incidence here is pretty much equal to the angle of refraction, which is not what we expect. So that means that we don't see any bending going on at all. And if you look at the line, it's pretty straight. You don't see a lot of deviation. Here, when it's coming out, what do we expect? So we're going now from slow to fast. So we expect that the angle of refraction is going to be larger, okay? And it is, but the first part doesn't make any sense, okay? So we're going to rule that one out. That one is a no. What about this one? Again, so we're starting off, we're going from fast to slow. We expect to see a large angle of incidence and a small angle of refraction. That's not what's happening here. Second one, we expect to see a small angle of refraction and a larger angle of incidence. That's not what's happening. We expect to see a large angle of refraction, because it's going to air, so it's supposed to speed up and get faster. When we go from slow to fast, we expect to see a big angle of refraction. And it's bigger, but this part again here, this doesn't make any sense, so we gotta rule that out as well. That's not what we expect to see. What about here? D, okay? So we ruled out A, we ruled out B because they're not following those laws of refraction. They're not behaving the way that they're supposed to be. That diagram doesn't say what corresponds to these rules of thumb, okay? Not rules of thumb, they're laws. So here, let's look at this one. So we're going from air to glass, so from fast to slow, okay? That makes sense. That first part looks good. We expect that the angle of refraction gets smaller when we go into the more dense medium, the glass prism. But then, what happens here? When it's coming out, now we're going from slow to fast, we expect to see a large angle of refraction. And this one is emerging on the normal, which is no angle at all, no angle of refraction at all. So that part doesn't make any sense, and we're going to have to rule out D. So let's look at C. So here we have a large angle of incidence when we're traveling fast medium. When we're going to the slow, it decreases, so we have a small angle of refraction. That's what we expect to see. And so now when we're going from slow to fast, we expect to see a large angle of refraction and a small angle of incidence, and we do see that. This makes sense. This is our answer, C. All right, continued in the next video.